In the second half of Unit F of Algebra 1, students continue to solve quadratic equations with new methods, completing the square and the quadratic formula. In this video, we'll be taking a look at Lesson 12, Task 12.3, which is the Introduction to Solving Quadratic Equations by Completing the Square. Take a moment to read the task and also the problems that students are asked to solve. Earlier in Lesson 12, students make the connection between a perfect square trinomial in standard form and in factored form. A perfect square trinomial, which is in standard form, which is on the left, will always factor into a perfect square, in this case, a binomial squared, on the right. To complete the square, students need to take a standard form equation, which may or may not be a perfect square trinomial, and they need to turn it into a perfect square trinomial by manipulating the constant term. Going back to our example, to complete the square, the quadratic equation does not have to equal 0. Diego took his constant term 9 and he subtracted it on both sides so that he has x squared plus 10x equals negative 9. This allows Diego to focus on the x squared plus 10x so he can turn it into a perfect square trinomial by adding 25 to both sides. From here, he combined negative 9 plus 25 to get 16. And he factored this perfect square trinomial of x squared plus 10x plus 25 into x plus 5 squared. May chose to keep the 9, our constant, on the left side of our equation, and she saw to turn this x squared plus 10x into a perfect square trinomial and needed to have a 25. So she saw that she needed to add 16 to both sides of the equation to get 9 plus 16 to equal 25. From here, she factored the perfect square trinomial to get x plus 5 squared equals 16. At this point, both students solved the quadratic equation by reasoning, by saying that a number squared equals 16, which in this case is 4 and negative 4. At this point, they see that x plus 5 equals 4 and x plus 5 equals negative 4, so they both end up with the answer x equals negative 1 and x equals negative 9. The illustrative math curriculum teaches students how to complete the square using the examples above. However, for this video, I will provide an alternate way to complete the square using algebra tiles, which offers students a visual representation of what is happening during completing the square. In this first example, students are asked to solve x squared plus 6x plus 8 equals 0 by completing the square. When working with algebra tiles, I like to use a mat that helps me keep my algebra tiles organized. So for this example, I have an x squared, I have 6 x's, and I have 8 positive ones, all on the left side of my equation. What I want to do is I want to turn these pieces into a square. When we have a square, that means that all the sides, the left side, the top side, the right side, and the bottom, are all equal. So I like to start off with my x squared piece and my x tiles to see if I can rearrange these so that I can turn them into a square. So I'm going to put my x tiles underneath my x squared and to the right of my x squared. And sometimes what I have my students do is just move one piece at a time. So right now I have x plus 1 times x plus 5. The side and the top are not equal, so this is not a square. If we move one more piece, that's x plus 2 times x plus 4, which again is not a square. If I move my third piece, I see I have x plus 3 and x plus 3 as the top and side, and that does make a square. Now to make this a perfect square trinomial, I have to fill in all of my tiles here. And if I fill in my tiles here, I have 8 pieces currently. So for my original problem, I actually don't have enough pieces to complete the square. I'm missing a piece. To fix this, so that I do have a perfect square trinomial on the left side here, I need to add an extra piece on both sides of my equation. Now I can see that this is a perfect square, and in factored form, if I go across the top and across the side, I have x plus 3 pieces and x plus 3 pieces, which is x plus 3 squared, equals 1. And for my problem here, I would need to ask myself, something squared equals 1. Well, I know 1 times 1 is 1, and negative 1 times negative 1 is also positive 1. So that means that this x plus 3 has to equal 1, and x plus 3 has to equal negative 1. At this point, I do need to solve both these equations for x, So we can do the inverse operation of plus 3 to do minus 3 on both sides. And I have 1 minus 3, which is negative 2. And if I do my other equation, I use my inverse operation of plus 3 to subtract 3 on both sides. I have negative 1 minus 3, which is negative 4, which gives me my second answer of x equals negative 4. My next equation is solved by completing the square is x squared plus 12x equals 13. So on my mat, I have my left side x squared plus 12x's equals 13 ones pieces. And again, I like to start off with my x squared piece and my x's, and I want to turn these into a square. So I like to have my students move pieces one at a time, or in this case, we might do 3 at a time just because there's so many pieces here. And we want to make sure that what goes across the top and what goes across the side is equal. So x plus 3, x plus 9, they are not equal. And I move 3 more pieces along the side here, so I have x plus 6 pieces and x plus 6 pieces along the top and on the side, and that's now a square with this piece missing here. On the right side here is 13. I'm not going to put these 13 pieces inside of my square because they are on the right side of my equation. My square is on the left side of my equation. Now this is the downside of algebra tiles. I would have to have a lot of pieces of algebra tiles to add to the left side and to the right side because I currently don't have any pieces on the left side to add inside of my square. What I'm going to do, because I do not have enough pieces for that, is I am just going to draw what my pieces would be by drawing lines each time an algebra tile ends. By drawing my lines, I see that I have 6 pieces tall times 6 pieces wide. So that means that I have to have 36 pieces inside of this section here to complete the square. If I'm adding 36 pieces to the left side, I also need to add 36 ones pieces to the right side. And again, I don't have enough algebra tiles for that, so I'm just going to draw a box here with 36 in it. And this means that my equation now becomes x plus 6 times x plus 6, or x plus 6 squared, equals 36 plus my 13 original pieces. In this example, this is very similar to what Diego did. At this point, before I figure out what number squared equals 36 plus 13, I'm going to add these two numbers together so that I know what the number squared should actually equal. 36 plus 13 equals 49. So that means that whatever number I'm working with, squared has to equal 49. Now I know that 7 times 7, or 7 squared, equals 49, and negative 7 times negative 7, or negative 7 squared, is also positive 49. So this means that x plus 6 has to equal positive 7, and x plus 6 has to equal negative 7. My last step here for both equations is to take the inverse operation of this plus 6, which is to minus 6, on both sides of each equation, so that I can get my final answer of x equals 7 minus 6 is 1, and x equals negative 7 minus 6 equals negative 13. For the last example for this video, we have 0 equals x squared minus 10x plus 21. On my mat, I have the left side is 0 because the left side of my equation had 0. The right side has all my pieces. And when you're completing the square, it actually doesn't matter which side you have your square on. Because the square is on the right side here, I am going to leave it on the right side. And notice how my x's are all red this time, and that's because we have negative 10x. The process is still the same even if you have negative 10x here. I am going to, again, move these pieces so that they have the same along the top and same along the left side of my square. So I currently have x minus 3 and x minus 7, which is not a square. If I move 2 more pieces, I have x minus 5 and x minus 5, which does make a square. So for the pieces that complete this section here, I need to be careful about the sign. So this is going to be negative times negative, which is a positive section here. So these 21 pieces are fine to go inside of my square because they are the correct sign. So I'm just going to take my 21 pieces here and use them to complete my square. And once I put all my 21 pieces inside of my square, I do see that I do not have enough pieces to complete this square. Unfortunately, I also do not have enough algebra tiles to complete this square, so again, I'm just going to draw the pieces in by drawing the outlines of what these pieces would look like. So to complete this square, I would need 4 additional pieces. I can't just add the 4 pieces to this right side here without balancing my equation, add the 4 pieces to the left side as well. So I'm going to draw my 4 pieces here. So when I have my square, I can see that I have x minus 5 times x minus 5, or x minus 5 squared, is going to equal my 4, or in the way this is currently written, it's 4 equals x minus 5 squared. Even if the square is again on the right side, we can still do the process very similarly to how we've been doing it. So 4 equals a number squared. Well, I know 2 times 2, or 2 squared, equals 4. So that means that 2 is going to equal x minus 5. I also know that negative 2 times negative 2, or negative 2 squared, also equals positive 4. So negative 2 equals x minus 5. To finish this problem, I will need to use the inverse operation of what is with my x. I need to use the inverse operation of negative 5. The inverse operation of negative, or minus, is plus. So I'm going to add 5 on both sides of my equation. So I end up with 2 plus 5 equals 7. 7 equals x is my first answer. And again, the inverse operation of subtraction is addition. So I'm going to add 5 on both sides. Negative 2 plus 5 is 3. 3 equals x is my other answer.